Alrighty guys, it's time to tackle Unit 3 of AP Chemistry. It's gonna be epic. I don't know why the heck I did Unit 3 after Unit 4, but what can I say? I'm just that kind of guy. Hello everybody, I'm Karar, and today we're gonna be talking about Unit 3, Intermolecular Forces and Properties. This is a one thick video, but we'll get through it, okay? So basically, just real quick, there's two ways this could go down, right? I could either do Units 5, 6, and 7, which I haven't done yet, or what I could do is I could finish this video, do Unit 6, which I haven't covered at all, and then I could do whatever I haven't covered already, because I have covered quite a bit in my other videos that are not necessarily full unit walkthroughs, but I don't want to repeat too much. So just let me know which one you guys want, whether you guys want me to go through 5, 6, and 7, or whether you want me to go through just 7 and then an extra video, and then I'll have more time to do maybe like a practice test for you guys, who knows. But let's get into the video, there's a lot to cover, let's do it. So the first thing we got to talk about are intermolecular forces. So basically, these are forces between molecules, okay? You can't say that they're intramolecular forces. Those are different. That's within the same molecule. This is between different molecules. And these, honestly, are way more interesting. Come on, who cares about those random covalent ionic bonds? Lame, okay? We're talking about intermolecular forces. So we'll go from weakest to strongest. First, we got London dispersion forces. And these are in all molecules. Once you understand how they work, it's a lot more clear why they're in all molecules and why they're also weak. So basically the way it works is if you have a sodium atom, right, and you got a bunch of electrons floating around, we'll only write one because that's easier to think about, and another one over here. So these electrons are randomly moving, right? So they're just moving around randomly, whatever. But what happens if this electron just randomly, for no reason, moves right here? Well then, we got a positive charge on this side, a negative charge on this side. While this electron wants in on the action, he's like, whoa, there's such an attractive sodium just hanging out there. So this electron goes over here. So this electron is connected to this one, this electron is connected to this one, but basically, now there's a force between these electron and sodium, because as you know by Coulomb's law, as you have a charge and they're closer together, there's more force between them. So just because this electron randomly went to the other side, it brought in this other electron because the other electron was more attracted to the sodium, now that this one's on the opposite side. So now the two sodiums are attracted to each other because the electron on one is attracted to the positive nucleus of the other. However, because it's random, it's very weak. Also, because the only thing it requires is the presence of electrons, it's in all molecules. Okay, the other thing we gotta talk about are the dipole-dipole forces, or DDs. And basically, this happens when you have a polar molecule, and basically, polar molecules are LDFs, but they're like permanent, kind of. Let me explain. So, if you have carbon monoxide, right, your oxygen is more electronegative, so it attracts the electrons more, and it'll have a negative charge. A small negative charge, very small negative charge, because it only attracts a couple little electrons. And then this one will have a slight positive charge. Then, if you have another carbon like this, so you might say, why are they even attracted to each other? This is a negative to a negative, shouldn't it be repelled? Well, basically what happens is, yes, it's repelled, but when it's repelled, it rotates instead. And then the carbon gets rotated closer. And now, you got the positive next to the negative, and now these guys attract to each other. Now, the reason why dipole-dipoles are stronger than London dispersion forces is because the dipoles are permanent. They're always happening, they're consistently attracted to each other. And you can clearly see why only it happens in polar molecules, because in a nonpolar molecule, these dipoles would not be permanent. Polar! Okay, and then the last one we got to talk about are hydrogen bonds. HBs. So a hydrogen bond is basically literally just a dipole-dipole force, except with a very big difference in electronegativity. Because the bigger the difference in the amount of charge they have. And the only way to get such a big difference in electronegativity is to have something paired with hydrogen. Specifically, nitrogen, oxygen, and fluorine, otherwise memorized as NOx. So any of these guys paired with hydrogen is going to have such a strong difference in charge. So the charge is greater, so by Coulomb's law, the force is greater, so hydrogen bonds are really, really strong. But unfortunately, they're only present in polar molecules with FH bonds or OH bonds or NH bonds. Okay, so there's basically a two-step method for determining which of these forces are in a molecule. So, first thing you gotta ask yourself, is it nonpolar or polar? So if it's nonpolar, then you have London dispersion forces only, and you end yourself there. Then, if it's polar, you're like, oh, it also has dipole-dipole forces. And then the second step is, does it have nitrogen, oxygen, or fluorine attached to a hydrogen atom? If it does, then it also has hydrogen bonds. Also, this only applies if it is polar. Like, if it's nonpolar and it has an OH bond, it still does not have hydrogen bonds. Okay, so why the heck are these guys relevant? Why do we even care that, like, molecules have intermolecular forces? Well, the first place it's relevant is in phase changes, right? So let's say we start with a solid, which is, like, packed together the molecules like this, and we want to change it into a liquid. To do that, we have to pull these molecules apart from each other. So, then it becomes a liquid, and they're just floating randomly. Who cares? all around. And then, to get to a gas, we had to separate them even more. So that's, again, has to do with your intermolecular forces. Stronger the intermolecular forces, it's harder to make it into a gas. So, eventually they get separated really far, and now they're all far from each other. Okay. Also, intermolecular forces are also responsible for like surface tension, capillary action, cohesion, all those cool water stuff, because water has hydrogen bonds, right? So it's really, really strong intermolecular forces. That's why it has all those cool properties. Alright, let's talk about phases, okay? So basically you might think there's 3 phases. Well, no, they're not actually. You might say, oh wait, there are actually 4. No, there's actually 5, okay? Well, there's probably even more, but the point is, they're not 3. But for AB chemistry, for all intensive purposes, there's only 4. The first one is plasma, okay? And plasma, the only thing you gotta know about it is that it's ionized gas. So if on the test it asks what's a plasma, just say ionized. If there was if this was a multiple choice test and it gave you the option ionized, then choose that option, okay? But unfortunately this year it's not. But who cares? Who cares? Alright, next is gas. And this is basically a fluid that expands to its container. A liquid is basically a fluid with fixed volume, and then a solid is basically just a thing with a bunch of molecules packed together and held together. Okay, so that's basically all you gotta know about phases, so let's talk about the transitions between the different phases. So the easiest way to represent this is on something called a phase change diagram. So basically on the y-axis you got temperature, and on the x-axis you have energy added. So let's say we start with a solid, right? As we add energy to it, the energy gets put into the molecules, and the molecules are vibrating faster or whatever. Since temperature is a measure of this vibration, it's a measure of the speed of the molecules, your temperature is going to increase as you add more energy. But what happens once you try to convert a solid to a liquid? Instead of making the molecules faster, it spends the energy breaking intermolecular forces. Hooray, intermolecular forces again. Wow, we're using the stuff we learned. Holy moly, that's crazy. So, because it's not going into changing the temperature, and rather it's going into breaking intermolecular forces, it plateaus. The temperature does not change while you're converting it from solid to liquid, liquid to gas. So if we thought about it this way, let's say we had a solid thing over here, and we added energy to it. Temperature would increase constantly at a constant rate, and then it would reach the point where it's about to turn into a liquid. Then it plateaus because the energy is going into breaking intermolecular forces. Once again, add energy, the molecules get faster, then it plateaus again as it gets turned into a gas, then it goes up. So this over here corresponds to gas, this corresponds to liquid, this corresponds to solid. So let's talk about the names of the phase changes. From solid to liquid, it's called melting. Liquid to gas is called evaporation. Gas to liquid is called condensation. Liquid to solid is called freezing. And then there's 2 other cool ones that you probably want to know. Well, not for the AP, but it's just cool to know. Gas to solid is called deposition. And gas to solid, oh whoops, I did the same thing twice, epic. Solid to gas is sublimation. Epic. Alright, let's look at the diagram in more depth, shall we? So basically there's 2 types of lines, right? There's these like kind of sloping up lines and there's flat lines. So clearly from the slope lines, you could tell that the temperature changes a certain amount based on how much energy you add. The thing that quantifies this is called specific heat. And it basically tells you the energy required to increase 1 gram of a substance by 1 degree Celsius. But I just like to remember the definition through the units, because the units are way easier to remember. You just gotta remember that the units are jam per gram Kelvin. What do they call this? Joules. I don't know whether I said jam or something, but yeah. Okay, joules per gram Kelvin. And if you want to do any calculations with it, basically all you gotta do is you gotta use the units. So let's say we had 1 gram aluminum, and we wanted to take it from 25 degrees Celsius to 35 degrees Celsius or something. Well, the specific heat for aluminum is 0.9 joules per gram Kelvin. So essentially, if you looked at this on the phase diagram, you know that at like normal temperature, aluminum is solid. So it starts at 25 degrees Celsius somewhere around here, then it goes to 35 degrees Celsius. And we want to find how much energy was taken to get it there. So we take our 0.9, and we want our answer in joules, right? So we got to get rid of grams and Kelvin. But since we're dealing with change in temperature, right? It's how much it takes to change the temperature. The change in Celsius is the same as change in Kelvin, because adding 1 degree Celsius is the same as adding 1 degree Kelvin. So in order to get rid of the Kelvin in the denominator, we got to multiply it by the change in degrees Celsius, which is the same as 10 Kelvin. And then we got to multiply by the mass, or grams, in order to get rid of this G over here. So you multiply by 1. And hooray, you get 1 gram canceled out with this gram, Kelvin canceled out here, and wablamo, we got 9 joules. Oh my god, that was crazy. Now, chemistry teachers like to teach the equation. I don't think it's useful, because once you remember the units, it's so much easier, but, like, the way they like to teach it is Q, which is the heat added, is equal to MC delta T, or MCAT. Well, I guess that's kind of catchy. MCAT, let's go. But anyways, M is your mass, C is your specific heat, and delta T is your temperature. To be careful for units, make sure they cancel out. Oh yeah, the other thing about just knowing the units is like you don't even have to memorize it. They literally give it to you in the problem statement. So like if you know how to use the units, you don't even have to remember this. Although you might have to write it out. You know, just remember it. It's worth it. All right, so we talked about the like upward sloping lines. Let's talk about the flat lines. So clearly, it takes some energy to convert the solid to a liquid. How much energy is that? It's called latent heat. But you also know that if you have more substance, right, it costs more energy to convert it from solid to liquid. So latent heat is for the specific amount of substance. But what about for like any amount of substance? What's the ratio? That is called the heat of fusion. And this is basically the joules per mole. How many joules of energy it takes to convert 1 mole of the substance from solid to liquid. For liquid to gas, it's called heat of vaporization, which makes sense, right? Because evaporation, vaporization, that one's easy. But heat of fusion is kind of confusing. The way I like to remember it is like if you weld two metals together, you convert them to a liquid at the borders, and then you fuse it. Okay, I don't know whether that helped at all. That's how I remember it. I'm sorry. But anyways, let's do an example, right? We have our 1 gram of aluminum, and we want to convert it into liquid aluminum. We want to melt it. So we first got to convert to moles so we can cancel out the moles. So the grams cancel out. The moles are in the numerator now. Now what is the specific heat of aluminum? Sorry, heat of fusion. 10.79, okay. So then we multiply by 10.79 and it said kilojoules per mole. So if we do this, then we basically get, what do we get? 10.79 over 27 is equal to basically 0.400. But that's 0.400 kilojoules, so that's the same thing as 400 joules. Nice. Now we're basically done with this, except like what happens if you wanted to take a solid that was at this temperature here and increase it to a gas at this temperature? Then you have to go through it separately. You gotta add in this segment, then you gotta add in this segment, then you gotta add in this segment, and then you gotta add in that segment. But we already explained how to do all that, how to calculate all that. You just gotta know how to add it up. Okay, there's another diagram that's relevant, is the PT diagram, or the phase diagram. The other one was the phase change diagram, this one's the phase diagram. So the one thing you gotta remember about phase diagrams is that it looks like a Y. For water, this line over here slopes backward, but for like basically everything else, it slopes over here. So the only reason why water is special is because ice is less dense than water, but it's not that relevant. Just know that water is the example of when it goes back. So if I ask you, what does it say about the liquid or solid? It basically says that the solid is more dense or less dense than the liquid. Because ice floats in water, right? But anyway, let's try to derive how this diagram works. So we know that as you decrease temperature, right, you should go from a gas to a liquid to a solid. So clearly, over here we have gas, then we have a liquid, and then we have solid, right? Because as we decrease temperature, we're changing from gas to liquid to solid. So this over here is gas, this is liquid, and then the left is solid. Okay, what else could we say? Let us say that this right here is 1 atmosphere. So we know that it's a solid, solid, solid as we increase the temperature, and then it suddenly melts, and it goes from solid to liquid. So if we drop down this line over here, that's a line, I swear, this is going to be 0 degrees Celsius, right? Because it's the melting point. It's where the solid turns into a liquid at 1 atmosphere. And then if we extend this line, it intersects the other side, and it turns from a liquid into a gas. So we drop this down, what do you think it's going to be? That's right, it's a boiling point. And this is a 100 degrees Celsius. Okay, other important points to know is this is the triple point because all three of the Y parts meet over here. And that's basically where liquid, solid, and gas could all live together peacefully and quietly and happily. Okay, then this over here is the critical point. Now above this point, very weird things happen because over here, it's neither liquid or gas, it's both. It's crazy. It's called a supercritical fluid, but like liquid and gas can coexist. It's really, really weird stuff. I do not even know how it works, but yeah. Above the critical point, weird stuff happens. That's all you gotta know. Okay, also, you're probably wondering how sublimation works. Like, when does sublimation happen? Like, there's no way to make sublimation happen just at normal pressure. Well, that's why you reduce the pressure to over here. Because then, if we draw out the line, it intersects over here. So, right here, at this temperature, it sublimates from solid to gas. There's no liquid in between. Alright, I think that's it. Let's move on. Now, the reason why this unit is really long is because we've got to talk about all the phases individually. So, the first phase we're going to talk about is gases. And basically, there's one equation you gotta know. Don't worry about the Boyle nonsense, Charles nonsense. Don't even worry about Avogadro's law. The only thing you gotta know is ideal gas law. PV equals nRT. This should be plenty to solve any ideal gas law problem they could throw at you, okay? This is the only law you gotta know. And basically, the other thing you gotta know is know how to explain it using kinetic molecular theory, or KMT. So let's quickly do that. Why does increasing the volume decrease pressure? So if you have a small volume, right? These molecules inside are hitting the walls really, really frequently, right? The pressure is going to be pretty high because every time a molecule hits the wall, it's exerting force on it, so it's exerting a pressure on it. But if we increase the volume, these particles are going to hit the sides way less. So if they hit the walls less, they exert less of a force, and thus the pressure is less. Makes sense. Increasing volume, decrease pressure. then why does increasing temperature increase pressure? Well, the reason is because these molecules start moving even faster and stronger. So they hit the walls more frequently because they're moving so fast, and they also hit the walls harder because they're moving so fast. Well, yeah, they hit the walls harder, hit more frequently because they're moving so fast. And thus, you increase the pressure. So basically, the three fundamental assumptions of kinetic molecular theory is first, all collisions are elastic. Second, there are no intermolecular forces. The reason for that is because if there were intermolecular forces, like they would cause each other to deflect without even touching each other, which doesn't make any sense. And then the third thing is that they don't take up volume. Like the gas takes up volume as a whole, but the individual particles do not take up a volume. Alright, so we're basically almost done with ideal gas law. The one thing you gotta remember is when does this make the most sense? Because real gases are not ideal gases, so we had to talk about when this applies. The way I like to think about it is when is kinetic molecular theory the most true? When are IMFs the most negligible? That's right, when it's moving really, really fast, and the molecules are really, really far apart from each other. So when are the particles really far from each other? Big volumes. And what does big volume mean? It means low pressure. Alright, when are they moving really, really fast? So fast that the intermolecular forces don't play much of a role. That's when your temperature is really high, right? So these are basically the three conditions where ideal gas law applies most. The way I like to remember it is just by logicking through it using the KMT. When are IMFs the least important? So the other thing you gotta know about gases is partial pressures. And literally this just says that P total, what the heck is total? The total pressure is equal to the individual pressures of the gases. So if you have hydrogen, carbon, and water vapor all together in one container, the total pressure is just the individual pressures of all of them. The way I like to remember it is P is equal to nRT over V, right? So if we add the different H2, CO2, and H2O pressures, we get NH2 RT over V plus NCO2 RT over V plus NH2O RT over V. And we know that the temperature and volume are exactly the same because they're in the same container. And then we get N tot RT over V if we factor out the RT over V. And then this clearly is just the ideal gas law. What is this equal to by the ideal gas law? That's right, P tot. So there's basically two types of questions they might ask. They'll give you like the total pressure and they'll ask you what is like partial pressure of carbon dioxide. So basically you just multiply by the mole fraction of carbon dioxide, which is NCO2 over N total. And that'll give you PCO2. The other problem they might give you is vapor pressure, so let's quickly explain that. You basically have water, right? And some of the molecules are moving fast. Not all molecules are moving slow in water. Some of them are just moving really fast and they're trying to escape. So some of these molecules will escape into the air. And like whenever something escapes, it exerts the upward force. Similarly, some of the molecules in the air are going to be colliding into the water. So some of the water vapor in the air gets converted into water once it collide into the water. So some of them are going down, some of them are going up, and eventually this balances. And the pressure, once it starts balancing, is called the vapor pressure. The one place where this is applicable is if you're trying to collect a gas, let's say carbon dioxide, over water. So if you're collecting a gas over water, some of the water is going to evaporate, right? Because only once the pressure is the right amount will the equilibrium be established. Basically when the pressure of the water is equal to its vapor pressure. So this is H2O, and basically in the question they'll be like, what is the pressure of CO2 if the atmospheric pressure is like P total? Then basically what you do is you take P total, you subtract the partial pressure of water, which is the vapor pressure, and hooray, you get PCO2, just like you wanted. Very cool. Alright, last thing we got to talk about for gases is the Maxwell-Boltzmann distribution. So on the y-axis you got the number of molecules that are at this particular kinetic energy, which is on the x-axis. So, like, for a really low energy gas, it'll look something like this. So you can tell this is the number of gas molecules. So there's a lot of gas molecules at like this intermediate Ke, but because it's cold, it's a pretty low kinetic energy. If you increase the temperature, then the molecules get more spread out. So there's going to be less of them in the middle, but they're going to have a higher kinetic energy, right? Because you increase the temperature, you increase their kinetic energy. So it looks a little bit like this. So the main thing to keep in mind when you're drawing Maxwell-Boltzmann distributions, it should be flatter, it should be more shifted over, and it should never intersect the x-axis. There should be an asymptote at 0. Okay, epic. So this is lower temperature, this is higher temperature, because you can see the average kinetic energy is higher. Alright, that's basically literally all you gotta know about Maxwell-Boltzmann distributions. Alright, let's move on to mixtures. There's basically three types, right? There's suspension, which is basically large particles greater than 500 nanometers suspended in a liquid. A mixture is basically a combination of two substances, but they're not like chemically combined. So in a suspension, you got a bunch of really big particles that are not chemically combined with the thing they're put into. So an example is like paint, because you got all the really big chunks in it, and then you got chocolate, or salad dressing, anything like that. And then a colloid has slightly bigger particles, 200 to 500 nanometers, and an example is milk. Now the reason why it's not see-through, why milk is not see-through, is because the particles are big enough to scatter light. It's called Tyndall scattering if you want to look it up, but it's not relevant to AP Chem. Okay, solution. Less than 200 nanometers. So the particles are really, really tiny, and an example is salt water. The particles are so tiny that the light just goes through them, so that's why salt water is see-through. Okay, so the most interesting of these three is solutions. So we're going to talk about solutions in more depth. First thing we want to know about it is what are the different types of concentrations. So the first one is molarity, which is basically going to be your your moles of solute, which is the thing you put into the solvent, over the liters of solution. Molality, on the other hand, is going to be your mole solute over kilograms of solvent. So it's important that you know the difference between solution and solvent. Solution is the overall thing. The way I like to remember it is because in a lab, your teacher's always like, put in this thing first and then dilute it until it reaches the right volume. You shouldn't put the right volume in and then put in the thing. For molality, it's not the case, that's why you use solvent. The other way I remember the difference between the two is something called mole-al-Carl. My boy mole-al-Carl, he basically tells you that Al is paired with K, so mole-al is kilogram, and then Ar is paired with L, so molar is liters of solution. And you know that the numerator is moles because there's a mole at the beginning. Okay, so molarity is relevant basically for any concentration you have to do for kinetics or equilibrium. Molality is relevant for colligative properties, and colligative properties basically mean the changes based on concentration. So the only thing that's relevant basically is boiling point elevation and freezing point depression. And the only way to remember this is to just say it enough time that it sounds right to you. Because boiling point depression just sounds wrong. You just gotta go boiling point elevation, freezing point depression, let's go, now it sounds right. Dude, I really can't even say the other one, it just sounds so wrong. And basically the way you calculate it is delta T, so whatever change it is, if it's boiling point it's elevated, if it's freezing point it's depressed. So it's basically IKFM, where M is your molality, Kf is just the constant they give you, and then I is the number of molecules your solute splits into. So like NaCl is 2, MgSO4 2, what's another example? MgCl2 splits into 3 things, so I would be 3. Okay, epic. One more thing we gotta talk about for solutions is how they work. So basically you have your solution, right? Your solvent, and then you chuck in some NaCl. So originally they're really close to each other and they're attracted to each other because they're connected with an ionic bond. But afterwards, what happens is that the water molecules get really attracted. They're so attracted that they split the lovers up, and then you got a bunch of water molecules attracted to the sodium. Okay, you know what? We're not going to go with the metaphor. I don't know how to do this nonsense. Okay. So basically sodium positive, right? So the oxygens, which are negative, are going to be attracted to it. And then the Cl is negative, so the hydrogens are attracted. Make sure you note which direction the water molecules are facing because that is actually relevant, okay? So if you look at the diagram, basically the first step, right, is you got to break apart the Na and the Cl. So you got to break up solute-solute interactions. But we also had to break up the water molecules from each other so that they get attracted to the sodium. Because if they're attracted to each other, they're not going to be attracted to the sodium. So we also got to break up solvent-solvent interaction. And then third, we got to form interactions between the water and the Na, water and the Cl, so form solvent-solute interactions. Epic. Now the reason why this is relevant to know this stuff is because, like, if a thing has a really strong solute-solute interaction, it's going to be a lot harder for it to dissolve, right? Because you have to break these stronger bonds. However, if it forms really, really strong, like, solvent-solute interactions, like in this case, water is really, really attracted to the sodium. So even though water is attracted to itself, it's even more attracted to the sodium. So the force required to break the solute-solute interactions is worth it, because then it gets a way bigger payoff when it gets to sodium. And in AP questions, they sometimes ask you which bonds are being broken, which bonds are being formed. In this case, hydrogen bonds are being broken between water molecules, and then like ion dipole forces are being formed between water and the ions. Alright, epic, that is all we got to talk about solutions. Let's move on to the last thing we got to talk about. The photoelectric effect. Basically what it says is that if you have an atom, right, the atom just chilling out, but it gets slapped by a photon just decides to run into it. Well, the atom, being mad, absorbs the photon, but it gets all of its energy. So now it's shaking with all this energy. What am I going to do with all this energy? What it does is it spits out an electron. Well, blammo, it doesn't want the energy anymore. Who wants to be shaking off of so much energy, dude? It's not worth it. So basically what happens is the photon's energy gets absorbed, is converted to an electron. But this electron takes a little bit of energy to break off. So we got to think about this a little bit. So what are the relevant equations? We got lambda f is equal to c, so wavelength times frequency is equal to speed of light, and then hf is equal to energy. So the Planck's constant, which is 6.626 times 10 to the negative 34, I could wrap this nonsense like a... What? Okay, I don't know wrapping terminology, but anyway. We multiply that by the frequency and you get energy. So we know that the kinetic energy of the electron is basically equal to the energy of the photon, which is HF, minus whatever energy is taken to get the electron off the atom, right? Because you know ionization energy exists, right? So it takes some energy to get it off. But the rest of the energy of the photon goes into making the electron go at a certain speed. So the kinetic energy is just equal to HF minus the ionization energy, which we will call the work function, which is symbolized like that. And basically the reason why the work function is relevant is because below a certain energy of photons, electrons just won't get emitted because it's not strong enough to make it get kicked off. But then above a certain cutoff, the photons are strong enough in order to get the electron off. The other thing you should keep in mind is that the energy of the photon is only dependent on the wavelength or frequency. It does not depend at all on the intensity of the light. Intensity of the light is just the number of photons, okay? So if you increase the intensity, maybe you'll get more electrons, but you're not going to get like higher energy electrons, okay? Or if you're not satisfying the cutoff, increasing the intensity of the light as much as you want, it won't make electrons show up. You have to increase the frequency of the light. Alrighty, that's basically all we gotta talk about. We made it! Let us go! Hooray! Dude, I recorded this video like 3 times because every single time I got technical difficulties. First time, my microphone recorded 2 things. Second time, my microphone just turned off randomly in the middle of the recording. But this time we made it. Holy. Alright, if you guys enjoyed the video, leave a like and subscribe for more. Thank you guys for watching so much. Let me know if you guys want more of these kind of videos. But other than that, thank you guys for watching again. See you guys next time.